Alright, let's talk about half-life, and I'm not talking about the video game. In kinetics, the half-life is a time period. It is the time required for the concentration to fall to half its initial value. Alright, for example, if you start with a 1 molarity solution for your reactant, we're simplifying it to talk about a reaction with only one reactant. If you start with a 1 molarity solution for your reactant, however long it takes for the concentration of that reacting species to fall to 0.5 molarity, that time period is the half-life. The half-life is most interesting when we talk about a first-order process. So let's specify a first-order process. And for a first-order process, you may recall that the integrated rate expression looks like this. At the half-life, this is the time period, so now I'm looking at T1/2. At the half-life, the initial concentration falls to half its value. So the concentration at times T would be 1/2 of whatever the initial concentration is. If I plug into this equation, this first-order equation, substituting in T1/2 for T, and substituting in 1/2 of A0 for AT, my expression looks like this. Algebraically, my A0s are going to cancel. I have the log of 1 over 1/2. That is the log of 2. You can check the algebra on that yourself. The log of 2 equals K T1/2, and so the T1/2, the half-life for a first-order reaction, is equal to the natural log of 2 over K. You'll notice that this value for half-life, this formula for half-life, only depends on the log of 2, which is a constant numerical value, and the rate constant K, which is a constant numerical value for a particular reaction. The half-life is a constant for a first-order process. The half-life stays constant regardless of the initial concentration of material. Turns out this is very useful in processes such as radioactive decay processes. A radioactive decay is always runs by first-order kinetics, which means that the equation that governs the disappearance of the radioactive species follows first-order rate law, and the half-life is always a constant numerical value. So you can find the half-life for a first-order process, it's a constant numerical value, by plugging into this equation. The T1/2 equals the log of 2 over K. If we go to a second-order process, the half-life isn't as useful, but we can still figure out the half-life for a second-order process. Alright, this was our integrated expression for our second-order process. The half-life is still the time required for the concentration to fall to half of its initial value. And so at our T1/2, at our half-life, the concentration at time T will be 1/2 of our initial, just like it was for first order. That definition doesn't change. So let's plug into this equation and see what we get. Alright, what we see here happening is that my A0, the initial concentration of A, does not cancel. So our half-life, forgot my 1/2, our half-life, our T1/2, is still going to have an A0, an A0, an initial concentration of starting material present in the calculation. So let's clean it up and see what we end up with here. Alright, so finally we have an equation for the half-life of a second-order process. We specified that we're talking about a second-order process, or else this equation doesn't work. Our half-life is calculated as 1 divided by the rate constant, also divided by the initial concentration of your starting material. So the half-life is going to change depending on what your starting material is. Again, not nearly as useful as in a first-order process, but you still might have a second-order process where you're given some information about a half-life. So there we can see how this works. All right, let's go back to our equation for a first-order process. Our equation for the first-order integrated rate expression looked like this. And you'll notice that based on this equation and how it was derived and the origin of it is that we're talking about concentrations. That's what these brackets mean. In this expression, if it happens to be a first order process, I have the concentration initial divided by the concentration after a certain time. The concentration is a molarity, so I've got a ratio of molarity to molarity inside that logarithm. Those units cancel. When I take the natural log of that ratio, it's unitless. Those units cancel because I have the same unit on top and on bottom. Recall that molarity is moles per liter. So really, I have a moles per liter over moles per liter. If my reaction is in an aqueous solution, the liters are not really going to change as the reaction proceeds. So numerically, this value for liter on top and this value for liter on bottom are essentially the same, and so they cancel. So I could work this problem, instead of taking the ratio of the concentrations, I could take the ratio of the moles initially divided by the moles after time period t. Well, moles is not typically something that we have measured, but grams is. And recall that if I take the moles and divide by the molar mass, the molecular weight, that is my grams. And moles divided by molar mass over moles divided by molar mass is grams over grams. So essentially, if I have grams over grams, the grams initial divided by the grams after time t, that numerically is the same ratio as molarity to molarity, which means instead of concentrations in this original expression, I can do actual masses. And so often we see this equation written like this, where it's implied that these A's could be molarities, they could be moles, they could be grams. So grams initial divided by the grams at time t equals kT. This is often how we express first order processes, especially if we're talking about something like a radioactive decay process that we were just talking about with the half-life. A radioactive decay process is a first order process, and we commonly have at our disposal the initial grams of radioactive material, and we're interested in the grams after a certain time period. So this equation numerically is exactly the same thing as if we were doing concentration. Instead, we can do grams to grams for our ratio. Works out the same way.